Hello my friends, this is lecture 12, basic circuits and Kirchhoff laws. Simply about understanding basic circuits, how to apply Ohm's law to solve for some values, and understanding Kirchhoff's laws as well in a basic circuits. First part talks about circuit elements. As we draw a circuit, this circuit here would be a regular, how overall a circuit would look. We have a resistor, capacitor, and a battery here, and as we symbolize this circuit, here is what we would have, how we would show them. So each circuit element, we use a symbol to simplify and draw a circuit and solve for the values that are needed. Here is how everything is symbolized: a battery, a wire, and resistor, switches are symbolized a line, and this actually simpler version. Here we go. Capacitor, two parallel lines. A junction would be, of course, two wires intersecting each other, and light bulbs we show in this fashion. To light up a light bulb, the charges should start from positive side, go through the light bulb, and end up in the negative side. If that is not happening, the light bulb will not light up. So we need a current passing through it for it to light up. So this one will not be lighting up because it's not a complete circuit. Several questions talking about how you draw a circuit diagram. Parallel plate capacitors to parallel lines, and then we draw the same lines connecting. So this part here should look like over here, and so on. We have a resistor there. So hopefully you'll get used to symbolizing circuits. This time we have resistors here and there. 50 and 100 are along a line, so we should show them that way. That would be the best clue to get. And the 75 one is connecting with both of them at both ends. So I try to find the one that has 50 and 100 in a longer line, and 70 connecting to them on both sides. So A is my option here. Kirchhoff laws talks about currents and total potential difference in a circuit. The current related one is called junction law. We discussed this in the conservation of current or conservation of charges part as well. Current into a junction is equal to current out of a junction, so we add the in current, which will be I1, and this junction over here is equal to out current I2 plus I3. Loop rule states that in a loop, in any part of a circuit, if we add all the potential differences, total potential difference in a loop is equal to 0. Some potential will come out as negative, and we have to be careful about defining what potential is negative. And this is how we define it. As we walk along our loop, we will be adding all the potential differences we see all around this loop. And if I have a battery along my way and I am walking towards this positive side, I take that as a positive potential difference, so delta V1 here will be positive. As I'm walking across the resistances, this could be a resistor or a light bulb or any other device, they all have some certain internal resistances. And I'm walking along the same direction of current. I'm walking from high potential to low potential, so I'm going to take this delta V as negative. So across a resistor, I'll be taking the potential difference as negative if I'm walking in the same direction as current. Same thing here, I'm walking along the direction of current, so it's plus to minus. This guy will also be minus. and so on. The same thing here, minus. That's the idea. And this page summarizes that. Choosing the sign of potentials. You're walking towards positive. This guy is positive. You're walking here towards negative. This guy is negative. And for a resistor, I'm walking along the same direction as current. I'm walking towards the negative. Delta V of the resistor is negative. And from Ohm's law, we can write this as I times R. It's negative, so we put the negative sign there. That's overall what loop law is. I'm going to skip this page here. It's about the same idea. But I'm going to go to an example here. What is this current over here? That's what the question is asking us. What is the current passing through a 200 ohm resistor? So junction rule, current in is equal to current out. When I say that, I mean the total current in is equal to total current out. If I call this guy I1, call this guy I2, and assume this guy has a current I3, well, we're looking for that current. It's down. In current to the junction, first I define my junction. Here's my junction here. I can choose any junction I want to reach where I want to reach. But over here, it's obvious that this is my junction. I want to play around to find my currents. I1 comes in, I2 and I3 goes out, I3 continues here. So In is only I1. That's equal to I2 plus I3. And if I solve these, input in all the known values, I'll find I3 as 1 ampere. 2.5 going in, 1.5 going out, and the other one should be 1, so they will be equal to each other. In is equal to out. And the full solution is also given here. The current through a 3 ohm resistor is over here. I would use a loop rule to find it. I would be going in this direction. That would be my guess, because this power source epsilon 1 is larger than epsilon 2. So minding the fact that current is plus to minus, this higher power direction would be enforced into the system, and it should be this way. The 6 volt would be trying to generate current in the other direction, but it's weaker, so the stronger power will win. That's what I'm guessing. If I'm wrong, I would find my current as negative, and I would just go ahead and say, okay, it's in the other direction. I was wrong. So we choose a direction of loop, and we apply the loop rule. Total potential difference equals 0, or delta V total, as we like it more. I'll put it as delta V total equals 0. And I'm gonna be walking along here. I'm walking towards plus here, so epsilon 1 will be plus. I'm walking along the current here, the same direction as current, so it's plus to minus. I'll have minus I times R. That's my delta VR actually. And from Ohm's law, I'm writing it as I times R. Let me write that better. I times R, and it's negative because I'm walking towards negative. So minus IR here. And the epsilon 2, I'm also walking towards negative, so it will be also minus. Once I put 9 volt here for epsilon 1, I times R, and 6 volt for epsilon 2 equate to 0. And solve for I'll have I times R equals 6 volt. I'll have 3 volts here, taken to the other side, and so on. Algebra, I'll leave it to you to solve. And the current will be 3 volt divided by R. R is also 3 ohms, so I'll have 3 volt over 3 ohms, 1 ampere. This question is a similar one. I'll leave this up to you. We'll look at it again in an LC session. I'm going to pick a loop here. I'm going to find this current passing through this guy. Sorry, there's a current in 1 ampere in the following circuit. Current is given actually, and we're asked to find the resistance. So current is 1 ampere. It will be in this direction, obviously, plus to minus. And we have just one loop, all the resistances in this loop, which are actually connected serially. We'll get to that soon. We'll have the same current. Applying the loop rule, total delta V total is equal to 0. We'll walk along. We're walking towards plus. We have 1 epsilon, so I'll call it epsilon. Maybe call these R1, R2, and R3 here. And walking along the current, I'll have all negatives, right? For IR. So I'll say epsilon minus I times R1 minus I times R2 minus I times R3 equals 0. And putting in the values known, epsilon is 9 volt, I is 1 ampere times R1, that's minus, not equals. So 1 ampere times 3 ohms, I R1 minus 1 ampere times 2.5 ohms minus 1 ampere times R3 equals 0. And you'll find your current. Again, we'll get back to this later. Series and parallel circuits. In a series circuit, every battery will have the same current because we have only one line passing through every one, and there's no other path my current can go. So all the same current. If I call this guy R1, this guy R2, this is the symbolized circuits we see here and there. Currents will be equal to each other because we have just one line current can go. So I1 is equal to I2, and they're all equal to one current. We can call I total here. Potential differences are shared. So for a series, currents are the same. Potential differences, let me call this voltage, it will be shorter. Voltage is shared. They will share this epsilon depending on their resistances, and I1 is equal to I2. And they are equal to I total. For a parallel circuit, we will have an I total here, and they will divide into 2, I1, I2. I1 will not be equal to I2. And from junction rule, I can say I total is in equals to I out, I1 plus I2. But they have the same potential differences. So if I put a voltmeter here and measure delta V2, and put another voltmeter here, measure delta V1, they will be equal to each other. and each actually is equal to epsilon. All the parallel arms will have the same potential differences. So we can safely write for a parallel circuit epsilon is equal to delta V1 equal to delta V2. And they share the current. We say I total is equal to I1 plus I2. So in a series circuit, currents are the same, potential differences shared. So if I measure also potential differences here as delta V1 and delta V2, it became too much cluttered, but I will say epsilon is equal to delta V1 plus delta V2. And in a parallel circuit, the potential differences are the same, current is shared. We'll get back to these questions here in the future, but if I think in terms of a lone light bulb and in series 2 light bulbs and in parallel 2 light bulbs, I'll find the lone light bulb will be brighter than those two in series. So A is larger than B and B is equal to C. In the left quick check question, on the right they all have the same brightness, the same current passing through them, and we'll get to a point where we understand why that is the case. But what will happen is, if I have two parallel bulbs in the same power supply, they will draw twice the current from the power supply and they will share it equally, so they will have equal current with the first lone bulb here. Determinant brightness depends on the power, and power here is described simply by I squared R. So when I know the current passing through a resistance and the resistance, and I can calculate power, high brightness, or a better brightness. I can also calculate, this is Ohm's law. I can also calculate power using this equation here, or that equation there. These are all replacing values using Ohm's law, that's all. Series circuits, again, they have the same current because we have one system here. I'll call this I total current drawn from the power source, and that will be passing through each. So I1 is equal to I total, and I2 is equal to I total. One can prove that the total resistance will be the resistances added. So if this guy has R, this guy has R, in the first circuit we have R, in the second circuit we have 2R. When we add them, we will call them the total resistance R equivalent, R plus R, 2R. If we apply Ohm's law, I is equal to delta V over R. To this circuit, we have delta V equals to epsilon, just one object in here, so it uses up all the power, divided by R. That's our initial current. And the second one, if I want to find the current, total current, which is equal to each current through each resistor here, total current will be delta V total divided by R total, or R equivalent. So I will have delta V total is the same. This guy is delta V total. Epsilon divided by R equivalent, 2R. So if this current was I, this will be I over 2. And therefore, in a series circuit, we have this case. First one has current I. The second, when I add one more resistance, current becomes half as much. So we have less bright light bulbs using the relation that power is equal to I squared R. High power, brightness is more. We'll have less bright light bulbs in the series circuit. For a parallel circuit, so in summary, Kirchhoff's loops rule and so on still applies in a series circuit, but we can derive from Kirchhoff's laws. We can easily define the equivalent resistance as this, add in the resistances, and then calculate total current using epsilon over the equivalent resistance. So this is the general definition for add-in resistances to find the total resistance or equivalent resistance for a series circuit. What is the total current drawn from the power source? That's the question here. I'll call it I total, and that's always equal to delta V total divided by R equivalent, and this would be my delta V total here, 12 volt. So what I'm going to do, I already know delta V total. I'm going to find this guy, insert in, and find I total. What is that guy? What is R equivalent? I have two resistances here, two resistors, and two different resistances, and I'll add them because they are in series. R equivalent is equal to R1 plus R2. That's 12 ohm plus 6 ohm, 18 ohms. And inserted in there, I'll have, let's carry this here. I total is equal to 12 volt divided by 18 ohms. I can find it as a number, but these are given as fractions, so I'll divide each by 6. 2 times 6 is 12, 3 times 6 is 18, so I'll have 2 over 3. Volt per ohm, is ampere, or current is ampere. So answer is 2 over 3. This is a very similar question here. The diagram below shows a circuit with 2 batteries and 3 resistors. What is the potential difference across the 200 ohm? I'm looking for this guy. Let me call this delta V2. Let me name everybody. I'm going to call this guy R1, this guy R2, and this guy R3. I'm going to call this epsilon 1 and epsilon 2. I have 2 batteries here. For the whole system, I have a total delta V total. Adding these, they are connected in a correct way of minus plus. Remember, we add them. So delta V total will be epsilon 1 plus epsilon 2, 7.5 volts. And I have here, sorry, these are not resistances given, these are potential differences. Let's change those. And I have here given 2 potential differences and 1 resistance actually. 2 potential differences are delta V1, 3 volt, and delta V2, 2.5 volt. Now we stated that in a series circuit, currents are the same because we have only one line, and all the current should be passing through all the objects in our circuit, and that's I total. So I total is equal to I1 is equal to I2 is equal to I3. That's the case for series circuits. Let's put that down. And they share the voltage. Voltage is shared. How is it shared? According to Ohm's law. According to Ohm's law. Delta V is equal to I times R. That's another version of Ohm's law. If several resistances have the same current, they will share the potential difference in a way that the larger resistance takes the larger potential difference. We don't really have to play around with this idea a lot because we already know delta V1, delta V3 actually, not 2, and we're looking for delta V2. We said they share the potential differences, so we can write down delta V total is equal to delta V1 plus delta V2 plus delta V3. And that will give us our answer. What is the potential difference across? Delta V tot is 7.5 volt. Delta V1 here, 3 volt. Delta V2, I don't know. Delta V3, 2.5 volts. And I'll solve for delta V2. 7.5 volt equals 5.5 volt plus delta V2. Okay, run out of place here. Let's delete this part and go to next page maybe. And as I guess you would see the answer already. 7.5 is total, 5.5 is used, so delta V2 should be 2 volts. We could go ahead and quickly see this. They are shared 3 for 5.5 volt. Total is 7.5. 2 is left. But I want to go slowly and help you find this for harder cases. Could I use loop rule here to solve for my potential difference? Yes, I could. And go ahead and try it and make sure you'll find the same answer. This one is a series circuit with 50 equal resistances. So we will add them. 50 times R will be our answer. Epsilon is given. And we find the current passing through the system. Ohm's law. I'll call it actually I total. Passes through everyone. That's what we do with the Christmas lights. So I total is equal to delta V total or R equivalent. That's what we use here. R equivalent is this, and epsilon is 120 volt. We use that to find what the current is. Then we can use the current to find what is the potential difference across each resistor. We could also say, since they are equal resistances, each resistor has R, or each light bulb has the same resistance, they will share 120 volt equally. So 120 volt divided by 50, what each will get, because same current, same current, same resistance from this version of the Ohm's law. If this guy is same, this guy is same, delta V also should be same, so they will share it equally. Just divide by 50 would be also our answer here, would also work. That's not always the case though. If I have different resistances, larger resistance will get a larger potential difference for a series circuit. Parallel circuit, working on with the same ideas. We can find the current in a parallel circuit, actually how much total current drawn from a parallel circuit. Current will be shared because we have a junction and it will divide into two as I1 and I2, and they will have the same potential differences as we discussed already, all delta V. So for simplicity here I'll say delta V1 is equal to delta V2 equals the epsilon. Equal potential differences, different resistances, larger resistance will get less current from Ohm's law. Using Kirchhoff's laws again, we can prove that the equivalent resistance should be equal to that for a parallel circuit, but we won't prove it, we will use it. Currents, I battery here is what I call I total. Junction rule here tells me current in, right? This is my I in equals the current out, this is my I out, gives me one information. And I know they have the same potential differences. And I'll use Ohm's law to reach wherever I want to reach. I can always find the total current using total potential difference over R equivalent. This is how this is used in the book. I battery means the current drawn from the battery equals to total potential difference or voltage over total resistance, or I'll call it I total is equal to delta V total divided by R equivalent. And that's how we will solve our problems in this section. We already quickly reviewed this question. Here we have R, epsilon I is equal to epsilon over R. When we have two resistance in parallel and apply the equivalent resistance equation, let me do it in here, R equivalent is equal to 1 over R, and they have the same resistances here, 1 over R plus 1 over R to the power of minus 1. This will be 2 over R inversed. R equivalent will be R over 2. You actually add two resistors with the same resistance in parallel. R equivalent will be R over 2. 3, R equivalent will be R over 3. 4, R equivalent will be R over 4 from this equation. So that's the simplicity there. But we have potential difference epsilon here. This guy takes it, has a current epsilon over R. If I call that I and calculate the current here, I'm going to have epsilon over R times 2, so 2 times I. So double the current here. So if I have a parallel circuit, the current drawn from the power source is larger. If I have two equal resistance parallel, in this case it will be 2I versus I here. Now from this first light bulb, the current passing through is I. And the second case, I have a junction. It will divide into two, and it will divide into two equal currents if I have equal resistances. Let me draw that with a blue so we'll distinguish I and I. Why? Because I have a parallel circuit. They have same potential differences across. Delta V1 is equal to delta V2. And then find in current I is equal to delta V over R from the general equation. If this diode is the same, large resistance gets the lower current as we discussed. If they have the same resistances for this case, then they will have the same current. So they will equally share here. Therefore, I have current I here, passes through this guy, brightness is a power P, I squared R. I have current 2I here, divides into two equal amounts, junction rule, 2I, and we have same resistors, so they will share it equally. And they will have I passing through them, a power, the same. Power is equal to I squared R. Defines brightness. They will all have the brightnesses, same brightnesses. So that's a parallel circuit. What things about the resistors in the circuit are the same as we discussed? Potential differences are the same because they are parallel lines, always have the same potential. Actually, in this case, it's also the same here. They are all equal to epsilon. Be careful though, as we get to more complicated circuits, for example, there could be another resistance here, then things will change. Still, parallel arms will have the same potential difference. That will not change, but they will not always be equal to epsilon for more complicated circuits. This page is mainly talking about something I already summarized. We can apply junction rule, loop rule to define R equivalent to be this, and calculate that I can find I total using delta V total over R equivalent. This is done in this example here. Please go ahead and review it. Answer is given, solution is given, and we have these values. These three guys are in parallel. This one nicely summarizes how actually when we have more resistance, electrons have more paths to go through. So we should have higher currents, right? So it makes sense that we have less paths, 1 path, 2 path, 3 more paths, more charges can flow, so we can have a larger current, which means we should have less resistance. It's like having more driving ways, so more cars can go at the same time. Very similar to that. Okay, this one is a pretty cliche. What is the total current in this system? We find our equivalent first, parallel. Our equivalent is equal to 1 over 12 ohms plus 1 over 6 ohms to the power of minus 1. I would multiply this guy by 2. I'll have 12. I'll have 3 over 12, inverse it, 12 over 3, 4 ohms. Go ahead and do this in your calculators and confirm me here. That would be my delta V total. I'm going to go ahead and call this guy I total. So I total is equal to delta V total divided by R equivalent. And I have 12 volts for my total potential difference and 4 ohms for my R equivalent. So I have 3 amperes. Let's move a bit further here. I have this 3 amperes here. As it comes here, it will divide into 2. And it will not divide into 2 equal currents because I don't have 2 equal resistances. But I have this general Ohm's law, delta V over R. I know parallel arms has the same delta V. So this guy is same for 12 ohm and 6 ohm. Larger resistance gets less current. In fact, twice the resistance, I'm going to call this R1, will get half the current, R2. So if I have 3 ampere, it will be divided into 3 parts. This guy will take 2 of that, so 2 amperes, and this guy will take 1 ampere. N is equal to R at this junction. That should be confirmed by my solution, and it is 2 plus 1, 3 ampere, 3 ampere. Or I can just go ahead and say this. This is epsilon here, or delta V total, right? And all these arms are parallel, so I can say delta V1 is equal to delta V2 is equal to 12 volt. Then I can go ahead and apply Ohm's law separately. I don't know, I1, because it's not always as easy as this one to see that I have 12 to 6, twice larger resistance, half as current, so I might need to calculate them. What I do is, I know delta V1, I know R, I can calculate I1, right? I go ahead and do it. I1 is equal to delta V1 over R1. 12 volt over 12 volt. 12 ohms equals 1 ampere. It should give me the same answer. And the same goes for I2, right? Delta V2 over R2, 2 ampere. So I can go both ways. I can go logical, divide my current, again twice the resistance, half the current's inversely proportional. I can use that. Or if I can't see that, I can say they have the same potential differences, define that 12 volt in this case, and use Ohm's law individually to get to the currents. So when the switch closes, what happens to current? We will have a parallel system. Our equivalent resistance will lowers, and thus current increases. Why? Because of Ohm's law, delta V over R, delta V is the same, and so on. We discussed this already. There are some similar questions. It's already quite a long lecture. I'm gonna leave it at that. Very similar ideas here. What happens to the light bulbs if I close this, and so on. This one is actually interesting. If I close this here, I give the current a very easy path to pass. So V goes out, and the current only goes through here. Very easy circuit. We call this a short circuit actually. And then we have a summary, how it looks, and the values for series and parallel circuits, which marks the end of this lecture. See you on the next one.